Hello. Okay. Okay. Yeah. Welcome everyone. Yeah, I guess this was the last addition to the schedule, but I'm happy that you found yourself here. My name is Lautaportti. I work for Enquos, and this is actually the talk version of the lightning talk that I gave yesterday on Cassandra, the database. And just a few words about myself and my company. So I work for Enquos at the moment. I've basically worked primarily with Python for the last 10 years, doing various other languages before that, Perl and PHP and that kind of stuff. I primarily do web development and sort of back-end background. Nowadays, I'm pretty much involved in the whole range of web development actions. And basically, I've been using Zoe, Plone, and nowadays Pyramid mostly for that. So I work for Enquos, and we're actually building a comprehensive health and fitness service with the motto "Living Well Your Way." And what we actually want to build here is a sort of comprehensive one place to gather all kinds of metrics about your physical and mental self, and provide a single service that takes that data, stores it very securely, and allows you to analyze the data on that service and take that data out as you see fit. So for this conference, the motto could be "Your data, your way." For building Enquos, we're using Pyramid, we're using Cassandra, we're actually using Elasticsearch and PostgreSQL for some services. And we're also launching a beta soon, and we'd like to welcome some technical beta users. And if you actually look at the porting to Python 3 book, there is a beta code that you can use within a week or two when we launch this beta. So please take a look if you're interested. Okay, so going into Cassandra. Let me just ask, were you at the lightning talk yesterday? Okay, so let's just go through everything. Do you know about Cassandra before? Have you used it? Okay, excellent. So just a little bit of background. What is Cassandra? It's a distributed database. It's written in Java, and it actually originated from Facebook. I think it was 2008. They were looking for a solution for their inbox search problem they had with huge amounts of data. And since that, Cassandra has become an open source project. It went through the incubator period at Apache, and now it's an Apache top level project. And it handles very large amounts of data very well. So the largest clusters that companies are using are hundreds of nodes, more than 500, and hundreds of terabytes of data that can go through that. And I think Cassandra has been said to have like the Google Big Data model, so column-oriented, sort of accompanied with the Amazon Dynamo infrastructure, which makes a excellent combination that Cassandra is. And Cassandra is highly scalable, high availability, high performance. So scaling-wise, you can actually scale it up linearly quite well. So as you add more nodes to the cluster, you can expect the throughput to scale up linearly, which usually happens in other databases for a certain amount, and then it just either stays there or bad things happen. But with Cassandra, you can go pretty far with that, and with that expectation. High availability, you can control the amount of sort of data redundancy you have, how much that is replicated, and each of the nodes in the cluster is independent, and as long as at least one has the data and you're willing to accept that, then the data is available. You can of course decide to have more strict requirements saying that you need that to be in 2 places or 3 places, but basically high availability is available there. And high performance, Cassandra is actually optimized for writes, so it does writes very well, but reads are also very, very fast. Currently it's being used by Netflix, eBay, Twitter. I'm not sure if they're using that anymore, but basically companies dealing with extremely large amounts of data. So two different aspects of Cassandra. There was like the big table data model and then the Dynamo infrastructure. So if we just first think about like the infrastructure side, the sort of decentralized nature of it. So the Cassandra database is basically always a cluster of multiple nodes. It's possible to run a single node cluster, if you just want to test, but it doesn't really make any sense since you don't really get any of the benefits. What's nice about Cassandra is that it can be made aware of your sort of multi-data center setup. So you can tell it about the topology. You can have a cluster in one data center, another, and when you interact with Cassandra, it knows about this, so it doesn't just like randomly pick a node and you pay up for the latency that you get, perhaps talking of the ocean or something like that. So it's very nice and it's very easy to configure and go from a single data center setup to a multi-one. And like I said, there's really no central server in Cassandra, and the nodes are logically equal. You can still have sort of different kinds of nodes, like perhaps storing different amounts of data on one node than another. But I think in the end, it makes sense to have it as symmetrical as possible. But clients can connect to any number of any of the nodes basically, and the one that you connect to, that will just act as a coordinator and just make sure that the dialogue within the cluster works. But you can just pick up any one. So it really wouldn't make any sense to always connect to a single one. And as such, you can say that Cassandra does not have a sort of single point of failure. Of course, depending on how you configure it and what sort of constraints you put on your queries. And you also get transparent replication, another thing that you can choose. But let's say a cluster of a given size n, you can choose any number between 1 and n on how many nodes you actually replicate the data. But that's up to you, and then that sort of plays part in the queries also. So if that was the sort of infrastructural side, then there is the data model. So the sort of infrastructure sort of just deals with the whole cluster and then finding the right place. And when we get to a single cluster, then that's sort of you can forget about the sort of network part in that case. So what it is, it's basically just a structured distributed hash table, so a dictionary basically. And the way the data is stored in Cassandra is that if you think about the address space of the dictionary, a given number of bits, then that space just gets split up in small ranges, and then each node in the cluster gets multiple ranges. This is actually a newer feature of Cassandra called virtual nodes. So if you've been using it before, they would actually get these continuous ranges that sort of just overlap so that you get the data redundancy. But the virtual nodes are more efficient, and I think it's easier and faster to actually change the cluster size. In that case, there is less effort to distribute the data in that case. And for each sort of logical data entry in that database, you always have a partition key. So that would be, if you think of a dictionary, that would be the top level key, and that's called a partition key, and that decides where in the cluster that particular entry will go. And it's always so that even though it's it's a cluster, it's many nodes, for a given data for a given partition key, it always is on a single node, so it would not be split within that. So that also gives you the sort of limitation that the data that you put under a single partition key needs to fit on a single disk on that particular node. And what I think is the one of the coolest features in Cassandra is the clustering part of it. So for a single data entry, you have the partition key, and then optionally you can have these clustering keys. And I'll have detailed examples of what that actually means. As I mentioned, the replication factor, that just determines the amount of data redundancy you have. So you can pick any number of nodes where you want that data to be stored. That can be one or up to the size of the cluster. But if it were the same as the size of the cluster, then even if there's a lot of work, but at least the data would be stored in many places. But of course, you'd be spending the most amount of disk in that case. Also, I mentioned that the data model is optimized for writes. So Cassandra works well with magnetic disks and also SSDs. But for magnetic disk, it makes sure that it doesn't do any sort of random seeks. So all the writes are sequential. And the files that Cassandra writes, they're append only. So that makes it efficient on magnetic disk too. Of course, with SSDs, it just gets better. So here's just an image from the Cassandra documentation. So if we think about the cluster as a ring, and basically here the ring is the address space that we have available. So that just gets split up into small ranges. And in this example, there's actually a 6-node cluster that we have, and we can just see that for each node, we've given 8 sort of tokens, or 8 ranges here, and you can see that they're not continuous. So B, E, and G, K. So this is how the virtual nodes work. And in this cluster, we actually have replication factor of 3, meaning that we store a single sort of partition key in 3 nodes. For example, A or B would be here. Where else do we have B? There is the second B. Node 4 there. So this is sort of how the virtual nodes, the sort of address space ranges, and replication factor sort of show up in the cluster. And for the pre-virtual nodes, you would just have these. It would have these continuous ranges in it. They would overlap, and you would just tell it the sort of beginning of the where the sort of range, the address of this, and you'd get replication or data redundancy from the overlap. But yeah, now virtual nodes are available, so you can use them. Okay, so that was a sort of overview of the two sides, the infrastructure side and then the sort of data model side. So I'm going to go a little bit deeper into the data model and how that sort of looks like. This is something I just sort of translated into just Python dictionaries. For me, that helped a lot to sort of understand and think about the data model. It doesn't really mean that it would be implemented as such. But basically, there are two ways you can store data in Cassandra. Say like the first non-clustered version is that we have a dictionary and we only have a single key, the partition key. And then that key can, hold a dictionary that has fields mapped to values. And then this key is the partition key that determines like on which node that particular entry goes. Or if you have replication factor which is larger than 1, then the same data goes to all those nodes. And then this part that's here needs to fit on a single node on the disk on that node. So that's the perhaps the simpler version. And then there's the clustered version. So it doesn't really change that much. We still have the partition key, but it's basically like a 2-level dictionary. And then the second key is actually a tuple that determines that. And what the clustered model means that it grows in 2 ways. So if you think about this, if you add more keys, it sort of just builds up vertically like a table. But in a clustered, we get something called wide rows. So for this one partition key, you can have as many of these clustering key combinations, and that sort of grows horizontally. And this is a very useful feature because what Cassandra does in addition, it makes sure that this data is sorted according to these tuples. So it's stored on the disk, so you can get ranges very effectively. So if you imagine this clustering key being a timestamp, then that data would be ordered by that timestamp. It would be very effective to get the last month of some data or whatever. But of course, it can be anything. It doesn't have to be a timestamp. But this is a useful feature for time series data. But for me, it sort of always boils down to these two options. Some data that you model sort of fits this, and in our case, what I've noticed, mostly it fits this. But you definitely use the two. Okay, this is just a sort of quick list about the sort of native data types that Cassandra supports. You got the basic stuff: text, numbers, booleans, blobs, timestamps. There's a field for like the IP address where there's 406. Particularly useful is the UUID, and basically you have a special case for UUID version 1, which is the version that contains a timestamp in it, in addition to the other parts. And then you can, use 4 just to get a random UUID. And this is very useful since, it's decentralized clustered, so you can't really, check for an existence of a key. So there's no like auto increment for a column that you sort of would like to have. So just creating a UUID, you're pretty much sure that you get a unique ID. You can store that. So these are particularly useful, and especially the version 1 that has the included timestamp in it. Additionally, it actually has collection fields. So you're going to have a column called something, which is a set, and these are typed collections. So you could say you have a set of strings or a set of ints, but you can't really mix. Same goes for a map, which is basically a dictionary of just key value mapping, and a list. And then you have operations that can operate on these, append or add or remove. And then there's one more, which is the counter column. It's basically a distributed counter that you can increment by some value. There are some limitations on how you can use that, but yeah, that's pretty much what it does. So those are the basic data types that are available to you. So then, from the developer's perspective, how you interact with Cassandra, there used to be a single way, which was the thrift generated API. That's basically an RPC. So you have a set of methods that you can call, and it's still usable today. You can use it. I think a lot of projects do. I think it was perceived as being slightly difficult to use, and sort of perhaps hard to wrap your mind around that. But now there is an alternative for that, which is called the Cassandra query language, conveniently CQL. So to make it difficult to talk about Cassandra query language and structured query language in the same talk. But basically CQL is very SQL-like, so it's definitely inspired there. The syntax is very familiar, so if you know how to use SQL, it's very straightforward to start using that. If you think about it from the syntax perspective, but if you sort of bring all the semantics in and what you sort of expect from a SQL-like query language, then you might get disappointed. So there are definitely some limitations just due to the fact how Cassandra models and what it tries to achieve. So basically there are no joins, there are no subqueries, foreign keys, ordering is limited. And that might sound a bit depressing at this time, but we have some examples. So basically the answer is that you just model in a way that you don't need them. But I'll have some examples of that. And actually SQL is currently in version 3, I think it's 3.04 or something, and that version is available in Cassandra 1.2 plus. I think 1.2.6 is the latest version of Cassandra. But if you're using version 1.1, you probably might get like SQL 2, which has a limited support of features. But currently in the latest version, you have data definition language commands, you have data manipulation language commands. There is a sort of data dictionary exposed by Cassandra, which allows you to introspect the cluster and the node just using SQL queries. There's support for tracing, which is very nice if you trace a query, because you always connect to a single node, and the data may or may not be on that node physically. So in the sort of best case it is, and it does a query there, or if not, it needs to contact something else. So you can get these detailed timings on how that just goes through and debug your queries. And that's really useful sometimes. One thing to note about Cassandra and CQL is that there's really not much difference between an insert and an update. So they're saying that inserts are actually upserts. So if you insert something and then you insert that again, it just gets sort of updated. So there is no unique constraint that would say that you can insert this. But you can still use updates. But I guess that might feel a bit confusing, at least in the beginning. Again, if you sort of bring your expected semantics from SQL to Cassandra. I have a few SQL examples just to give us a taste and see how these sort of map into the Cassandra data model, because it always makes sense to keep that in mind when you work with SQL. So if you remember the example from a few slides back, it was a simple Python dictionary, which was the non-clustered version. So this is how you would, define the table in SQL. Quite straightforward. I just put the emails being a set of text fields, just as an example of the collection field. Nothing really strange about that, perhaps besides the syntax. Primary key indicating the ID field. So the primary key ID just says that this is the partition key, again, meaning on which node it goes into. Inserts are pretty straightforward, fields, values. There is some special syntax for the collection types, and the pigments colorizer doesn't really like that, so it marks it as an error. But yeah, quite straightforward, and query is pretty much the same. So that almost looks like SQL. And what that kind of maps into in a sort of Python terms is that you just have this dictionary with a key that has a dictionary's value, username.guy, and emails would be a set. So quite straightforward. Second example is a clustered table. That was a dictionary with two keys, and the second part being a tuple of the clustering values. So we start the same way, but now the primary key has two parts, and this is where you have to know how this sort of maps into Cassandra. So however many parts you have in the primary key here, the first part is always the partition key, meaning the node, and whatever comes next will make up the tuple of the clustering keys. So in this case, we just have a single value in that tuple, and that is the timestamp, which is actually a time UUID type, which was the UUID version 1, meaning that it includes a timestamp in it. And it's nice because if you insert something in this table with exactly the same timestamp, the sort of rest of the UUID1 bits still give you a fair chance at unique values, depending on how it determines the other bits. And one additional feature that I just want to show here is the clustering order. So I mentioned that Cassandra always stores the clustered sort of data sorted, right? So you can actually then say, should it be descending or ascending on disk? You can still sort it the other way around, just saying order by something, ask, or disk, but you can optimize this. So for example, this is kind of an example of a time series data. Let's say if we wanted to keep track of what people do, actions, what they do, and when they do it. And usually we would probably query that, give me the latest, what did this person do the latest, like latest 100 entries or latest 30 days. So if we store this in descending order, it sort of facilitates that, and there's no shuffling around. We just read a continuous range from disk, and that's it. So this is what these parts do. As far as inserting goes, nothing really changes, so it doesn't reflect here. But then when we query that stuff, we can just trust that it's sorted accordingly. So I just select timestamp date of action and I just say put in the partition key, get 10, and those are the 10 latest because they're stored in descending order. So that's one way to take advantage of the Cassandra model and get efficient queries for date ranges. So yeah, in sort of Python terms, that would then lead to this dictionary. It should actually say action log here, but there's a partition key, and then we have another dictionary that has tuples as keys, which are the clustering columns now. We only had one, which was the time UUID, so it kind of shows up like this. But it's I specifically made this a tuple instead of just a string because you could have any number of them, and it's just sorted according to that tuple in that order. And then finally you get the actual data payload. And then Cassandra sort of maintains that these are ordered either ascending or descending depending on how you declared that. Third one is sort of extension of the previous one, because if you think about the previous example, it was clustering, so it was a white row, so it continues to grow horizontally, right? And it just keeps doing that once you add more actions and more things happen. Cassandra, was it 2 billion? Something like that was the limit on the number of sort of these columns in a white row. So, well, whatever that is, you might end up hitting that limit. So what you want to do is you want to shard that so that, at some point you get a new row. And so there is a limit to how wide the single row will grow. And that's what you can do with composite partition keys. So basically what we want to do is that we just store data in a single row for a single year. So we actually just wrap the first part, which is the partition key, in parentheses, and that means that it's actually composed of the user ID plus the year. So when you insert stuff and when the year gets to a new value, that means that the data gets recorded to a new row, and that limits it. So syntax-wise, it's quite a small change, and again, for inserting, there's really nothing special needed to be done. Cassandra itself, or the SQL driver, will map those and make sure it's like a composite key within Cassandra. And this was used much before SQL made this possible. You just first manually concatenate those two values, just make that a single partition key. But this makes it quite easy. You don't really have to deal with that, and sort of SQL layer takes care of that. And querying is pretty much the same. Now it just means that we have to always provide all the elements of the sort of a composite key. It would be meaningless to attempt to query anything using just the user ID because there is no such partition key. It needs all the parts. But this makes it quite easy for you to do sharding without having to sort of deal with that in the application layer, because just the year itself, the timestamp will sort of take care of that. But of course, if you want to query, many years worth of data, then you have to pull in all the keys or nodes, partitions that you're interested in. In Python terms, again, it's pretty much the same. Now I just put in a tuple in the sort of partition key. So it's still, for me, this makes much more sense than trying to map the sort of SQL and where there's a parenthesis or not. So yeah, so this is the one, and it's still the last change didn't really affect the clustering part of it at all. It's just a partition key that was different in this. A few words about I'm not sure if query properties is a good title, but just about interacting with it. So with all this cool stuff, we sort of have to give something away. So there are no full ACID guarantees. So atomicity, consistency, isolation, and durability. And basically, always if you do something for a single partition, single key, that's atomic and isolated. But if we're talking about a group of operations, you don't really get to expect atomicity or isolation. So if you do a number of writes, other clients can read and see, sort of read the partial write. There is, however, one sort of implementation specific guarantee. It's not really specified for Cassandra, but it's how it's implemented that guarantees it. And the way I've talked to people, it's sort of a accepted and expected thing, so it's probably not going to go away soon. But if you do multiple writes and they happen to have the same partition key, then those writes are actually atomic and isolated. So let's say you have like 3 tables that all have the user ID as a partition key. So it might, make sense that you have some sort of operation that actually writes into 3 sort of user-related tables, and you actually get atomicity and isolation for free. So you might actually take advantage of that as you design your tables. There is another option. There is this batch operation. So you can say, it's wrong to think about it as a transaction because it's not, but they use this batches things together, and you can tell that to be atomic, and you pay like a 30% penalty in terms of the, how fast that operation is. So, but Cassandra guarantees it's atomic, and but it's not isolated, so it's still possible that somebody actually gets to read some data in between. There's also another version of the batch, the unlogged batch. So you can still batch things together, so they actually go over the wire together, but then there are no atomicity guarantees, and then there's no penalty for that. For us, we've used batch for some things, sort of protectively. Maybe you could probably design around that, but it's good to keep these things in mind. Then there's just a few words about the consistency aspect. So Cassandra is always called, it's like eventually consistent, so the data will get there, but it might just not be there immediately. Usually eventual means a number of milliseconds, but it's eventual, it's not there. And it's also tunable, so you can actually choose what do you want from Cassandra. So you can choose this consistency level of sort of different options. I'll just quickly to show what they all mean. So let's say 1, consistency level of 1. When you make a query, this could be a read or write. At 1, you're happy when a single note says that it's written that, or it's returning the data. Quorums means that you need like majority, more than 51%. There are some, quorum is just that, and then there is some for the multi-data center setup. So you can actually say local quorum. So you're just happy with getting a quorum from the local data center without having to pay for the penalty of the inter data center latency. Each quorum means that you get the quorum from each data center, but sort of like separately. All is a sort of massive hammer. That means the whole cluster needs to sort of agree on that operation, and you get single node going down with all, you get an error because you wouldn't get the everybody's agreement on that. For writes, there is any, actually that sort of relates to hinted handoff. I'll talk about that soon. But basically you can do this. So for reads and writes, you can actually choose which is an acceptable level. I think quite many might go with local quorums. So let's say you have a replication factor of 3, so then it would mean that it's good enough if 2 out of 3 give you an answer. So you can allow one node, any node, to go down and still satisfy that requirement. But some people go with just 1 and just trust that the data will eventually get there. Writes are durable. So what Cassandra does is that when it gets write, it first writes that into a commit log, which is append only, and after that it actually updates its sort of in-memory views on the data, and then eventually the actual sort of persistent data on the disk. But if that node goes down, it'll just replay whatever is in the commit log. So the data will again get there eventually. Few features of Cassandra: there's read, repair, and hinted handoff. read repair is just something that when you read something, Cassandra, there's a configurable probability for Cassandra to send these read repair operations, and basically it just, from all the replicas, it just asks for the hash of the data, or the hash of the data and a timestamp, and based on that it'll issue updates on the replicas if they are out of sync, if they have an older data timestamp there. So basically it just takes care of that, the latest version of the data propagates in the cluster. But you can configure the probability of when read repair happens. Hinted handoff is a system to make the writes efficient. So in case, if you have a replication factor of 3, then the data sort of needs to go to 3 nodes, right? But if one node is down, Cassandra can store this Cassandra can store this hint that when it comes up, then one of the other nodes, or in the worst case the coordinator, will send it when it comes up. I think the default sort of time period for that is 10 days. So if you sort of have a node offline for more than that, then you sort of need to take sort of manual operations, just not to make it or not to make the cluster become confused. So the any consistency level is just that you would accept write to just be a hint. So it would not even actually be written in the commit log of any node yet, but you just store the hint. So that's like the weakest possible consistency level for writes. For reads, that doesn't really make sense. Okay, so we had the SQL, how to interact with Cassandra, a few of the properties of how the queries work, what you can expect. And so next I'm going to talk a little about just data modeling when you build your application. So I'm sure everybody's familiar with the relational model. So usually you look at the data, you normalize that, try to make it sort of as compact as possible. You don't like that to duplicate data. But with Cassandra, it's kind of the opposite. For Cassandra, the query patterns are important. So you would sort of think about what kind of queries do I need to make, and then you design the tables so that they make those efficient in terms of the clustering keys, and just knowing that data for a particular partition key is on a single node. So it's good if we can just involve one node in that query instead of having to talk to the whole cluster. So what that means is that you usually denormalize, and sort of, I'm not sure you should always, but sort of a rule of thumb is that you can actually think about one table per query, or sort of a query group, or a group of similar queries. And the goal is that you optimize the read path. So you involve only the part of the cluster that can contain that data that you need. And that's done denormalizing, so at the expense of disk space, but that's the cheapest possible sort of commodity to have. So from the denormalization, for me it kind of makes sense that I think about sort of primary tables that actually have the data. I think this is sort of the relational model kicking in a bit, and then you have these sort of extra tables that sort of facilitate these queries. But I guess you can think about that the way you feel comfortable. But in the end, you just if you're in a situation that it's kind of hard to query this, to make this query efficient with this table, and then you think of how should I change the table, then don't. Just create a new table that facilitates that query better, and you just store the data redundantly. And partitioning and clustering. So it always makes sense to think about the partition key and the clustering, and how the data would grow in terms of the vertical space, the rows, and then the horizontal space, which are the white rows, the columns. So in that sense, I think with the relational model, you can think about the data in more abstract terms, just normalizes, and then you can just expect to be able to make queries. You add indexes or something to make those efficient, but it's in Cassandra they're hand in hand. So it would be hard to start a project by first modeling everything and then sort of building up views or whatever that would do the queries. A few words about indexing. So, like I said, first thing to make, because indexes would, are there to make your queries efficient, right? So the first step is always just try to model it, so that the model itself, the basics of Cassandra, will provide efficient querying. And Cassandra does have something called secondary indexes, which allow you to like SQL kind of create index on this column, and you would get that. They're actually implemented as hidden tables, and just Cassandra makes sure sort of updates that asynchronously. Quite many people, I think even the docs, sort of do not recommend using them, at least like overly. So not just throwing in indexes to make things faster. Better to actually just create another table to facilitate the query that you wanted to create the index for. It says they're good for low cardinality values. So if you have a column that you want to index that has just a few unique values versus a larger number of rows or whatever that they point to. Yeah. So, but you can always just create new tables that act as these indexes to facilitate the queries. Okay, so a few words about Cassandra and Python. So Cassandra itself is written in Java, and I think the largest Cassandra libraries also, or most used and most well-known, are written in Java. So Python may in a way be like a second-class citizen at the moment, but there are definitely ways to interact with Cassandra through Python. There is a project called PyCassa, which is probably or worthy prominent way of interacting with Cassandra. It's a Thrift-only project, so it uses the Thrift API, and there's no SQL support in that. Then there is the CQL driver, just like that allows you to connect to Cassandra. You get a DB API cursors, and then that you can execute. It'll do the type shifting or translation for you. There is a project called SQL Engine, which is kind of an ORM, object resource mapper, I think in this case they're calling it. It's how would you say, what's the word I'm looking for? I think it's based on the Django ORM sort of a model. So if you're familiar with that, I think the query patterns and are quite familiar. So basically, you write classes that describe the model. It'll do the SQL work on that. And this is actually something that we are using in our project. So we've been involved in just bringing up SQL Engine up to the Cassandra 1.2 feature set. So it's in usable state, and there are people in the States and here in Europe using that. So if you want to try out Cassandra, that's probably a good place to get started with, especially if you're familiar with the Django ORM. It's actually probably based on the discussion that we'd have with the author, it's actually growing a few sort of SQL alchemy syntax-like query capabilities. I don't know, that's a matter of taste, I think, but there's both ways of doing that. At some point I remember seeing like a SQL alchemy dialect project on GitHub. I think it was very early on, but I think that would be an interesting idea, just to see how far we could actually make SQL alchemy interact with Cassandra just by providing a dialect for that. There are many parts that wouldn't really make sense that SQL alchemy would provide, but I'd still like to actually try that just to see if it makes sense or not. There's also in the latest Cassandras there's a Thrift API, right, which is based on the Apache Thrift project. It's an RPC. It's sort of quite general. So there is a new binary protocol that you can use to interact with Cassandra and through SQL, and that's asynchronous. You can actually have like multiple commands going on a single connection, and you can actually have server push messages up to you. So there is work on a Python driver for the binary protocol. It's going to be, or it's said to be, it's going to be in an open GitHub project within a few months. But there is a company called DataStax. That's one of the biggest Cassandra companies. So they're working on that driver. So within this year, hopefully, before fall, we actually have a good Python driver for the binary protocol. Yeah, and actually, let's go. Wanted to say something. So in terms of features, like the Java drivers, they have a lot of advanced features like, let's say, token range awareness. Because like you think about the cluster, the data is there according to the tokens in the ranges. So you can connect to any node you want, but it actually makes sense to connect to such node that actually has the data, because otherwise that node is just going to connect to another one to pull it from there. So if your driver actually knows how the tokens, how the ranges are sort of divided between the nodes, it could always connect to a node that has local data. I know the AstyNX, it's the Netflix driver in Java, and that at least has this awareness. I think at least for the non-virtual node distribution. So features like this are not available in the Python versions, at least at this time. Okay, at the end, just a few.
The nodes know between themselves what each node contains. Choose a random node.
No, the nodes know. So if you, if you contact a node, it knows whether it itself has that or who to connect. They have this custom protocol called Gossip that they talk to each other, and so they are aware of the sort of setup of the cluster. So Cassandra 2.0, that's in the works, and there are just a few features that's going to be in there. Compare and set, so you get these sort of inserts that you can check if it doesn't exist. There's I think there were like 3 round trips or something with the cast command, so there's a bit of a penalty there, but you can have these insert and update commands that take benefit of this. I think it was recommended you shouldn't really go overboard with these, but they might help with the sort of 1%, 2% set of problems that you might have in the app. Some other features in upcoming Cassandra triggers. I think those are pretty experimental. I think you have to write the trigger handle in Java or something to work with those, and those are probably going to change later on. I don't really know much about them. Improved compaction. So compaction is something that Cassandra needs to do to get rid of or to optimize the sort of data on disk and just get rid of eventually from deleted stuff. So there are different sort of strategies for doing that, and Cassandra 2.0 should have improvements there. And SQL cursors. So there's really no way to paginate through the query at the moment, so you have to do that in the app level, but the cursor should give you that ability to continue. Of course, there's no guarantees of isolation or things having not changed between those. And that's pretty much it.
Thank you.
You're welcome.
In your experience, how hard is to start up with Cassandra? I mean, install, configure, tune, also the learning curve required in the time. So if there are surprises, problems, or everything works easily from the start, what's your experience?
Well, when we started, we had the option of sort of deciding between the thrift, like the old way, the SQL, and we actually wrote some stuff first with Picasa, but then we decided to embrace SQL, and that was the beginning of the year, so it still felt a quite new thing, but I think that helped in the end. So SQL makes it much approachable. You know, if you have a relational background on that. We had a development team that Cassandra was new to everybody, but I believe that made it easy to approach, especially if you know use something like SQL engine that then sort of abstracts it a bit more. But so the SQL background is a sort of a blessing and a curse. So that might make you feel frustrated because it doesn't really do what you expect it to do. But yeah, I think nowadays it's very approachable. Of course, there are two different aspects: just the sort of application development, just modeling that, and then there's of course the ops side for maintaining the cluster and all that, which does require expertise. It's just like any other, of course. You have to know how to deal with. And one thing is, of course, that it's Java, so there's a lot of Java tooling. If you're familiar with that, then it should be no problem, or then you just have to learn that. But there are a lot of resources available. A lot of people are doing Cassandra and doing it very big, so there shouldn't be any surprises even if you scale up large, quite big and quite heavily.
So if I understand correctly, you had the action log table, right?
Yeah.
And in case you want some kind of a different query than sorted by the time descending, you would basically copy that data into another table, and then do the new query, which is optimized for the reads.
Yeah, write into as many tables as you want. So when you have something you want to record, then yeah, you could have multiple tables. We have something like, let's say like the action log. You might be interested to query what did this user do on this time, or who did this particular action, right? And it's kind of hard to satisfy that effectively with a single one. So you might actually, let's actually get back to that. Well, let's look at the second one. I think that's simpler. So here the action log user ID is the partition key. So you might actually switch those, so make the action the partition key or something like that. Then it's easy to pinpoint all the data that relates to that action, and then you can ask something else. But yeah, that's what I meant, that you just create those multiple tables that facilitate the different queries.
Okay, so basically like the development is like query oriented. First you know what to query for, and then you basically...
Yeah.
Yeah, okay.
Yeah, and that's kind of a sort of mindset switch also that you need to do.
Okay. Any other question? Thanks, Dan. Thank you.
Okay, thank you.